Hello, am I audible? Hello.
Yes, yes, sir.
Okay, so we can begin then. So welcome to another session of the problem solving sessions for NPTEL course Design of Electronic Converters, which is taught by Professor Shabari Nath. My name is Saleh Khan. I'm a PhD scholar at IIT Delhi, and I will be conducting these sessions on Saturdays. And so someone in the chat is saying that they are not able to access the recordings of the previous sessions. So in your portal at the left, on the left hand side at the end, you should be able to, you should have a link about problem solving sessions, and it will basically lead you to an Excel sheet which will have the YouTube recording link of each session. And it will also have a Google Drive folder wherein the PDFs of the sessions will be they will be available there. So if you're not able to get it, then you can email me. So I think I gave you my email last time. I will again write it in the chat. But basically, if you have any of the link to any of the recordings, it is in the same YouTube channel. So just go to the YouTube channel and you will find the other recordings as well. So I'm just putting my email. Okay. So uh, So, as always, we will begin with a summary of the content that was taught in the course for this week, and then we will do some problems or some uh, related to this week's content, just to give an example of the kind of problems that you will get in your assignments and exams. And this will not be exactly the same problems, obviously. And just to reiterate, I am not in contact with the actual course team. So if you have any issues regarding the assignment, you should put that in your uh, Q&A in the course portal. And I believe now they are answering the questions that are posed. So for the third week, the contents that were taught in the course. Firstly, we were continuing with the semiconductor devices. We had studied diodes and MOSFETs. So this week, the another main semiconductor switch was taken, which is the IGBT. And thereafter, we went to the another module, which is the gate driver module. And the gate driver concept was introduced, why it is required, and what should be the features of the gate driver. And then optocoupler based gate drivers were taken. And lastly, DSAT was also taught, but we will take that in the next session, problem solving session. So let's start with the IGBT. So so it is also a semiconductor device. It is current unidirectional, so it can only allow current to flow from the collector to the emitter, and not the other way around, not from the emitter to the collector. And this is different from the MOSFET, where the MOSFET has drain and source, and it can allow current in either direction if the gate voltage is greater than the threshold voltage. So the MOSFET is current bidirectional, but the IGBT is current unidirectional. So that is why if it is used in a circuit where you want bidirectional current flow, like an H-bridge circuit or a voltage source inverter, what is usually done is an anti-parallel diode is added to the IGBT. But for the MOSFET, there is an inherent body diode, as well as the channel of the MOSFET can conduct in the negative direction if you provide a gate supply. But both the IGBT and the MOSFET, they are both voltage unipolar devices. So next, another difference compared to the MOSFET is that the IGBT is a minority carrier device. So what that does is there are more charges available in the semiconductor. So it leads to a lower on-state voltage drop. So when the IGBT is on and there is a current flowing, the voltage drop is lower compared to a same rating MOSFET. So that is why we are able to go to higher voltage ratings, because as the voltage rating of the semiconductor increases, so you can basically crudely think about it that the semiconductor portion is increasing. And if the on-state drop is less, you can have a higher portion of the semiconductors so that we can block higher voltages, but the drop will not be that much. So that is why the IGBTs we have available for higher voltages compared to normal silicon MOSFETs. Silicon MOSFET, you will find it in the range of maximum 100, 200, 300 volts. I mean, there are higher voltages available, but they are specially crafted, or they are SiC MOSFETs, not silicon MOSFETs. But IGBTs, normal IGBTs, silicon IGBTs, they are available in higher voltages, up 1200 volt, even higher than that, 1700 volts. So that is because of this feature of their minority carrier capability. But there is, so this is the advantage, that we can have higher voltage ratings, but there is also a disadvantage. The disadvantage is that when you switch, especially during this turn off of the IGBT, these minority carriers, they have to be removed. So it takes more time to turn it off. So that leads to more losses during the switching time. So that is why for the MOSFET, for the IGBTs at higher voltage ratings, the switching frequencies cannot be as high as the MOSFETs. So, so there are advantages as well as disadvantages. So this was about the minority carrier aspect, and lastly, it is also a voltage control device. So if the voltage of the gate is more than the threshold voltage, the gate voltage with respect to emitter voltage, if it is more than the threshold voltage, then the IGBT will be turned on and it will be in the conducting mode. So now we can talk about some of the characteristics of the IGBT. And I will not go into detail because this is very similar to the MOSFET. I will just talk about what is different. So the output characteristics is again similar to the MOSFET. If the gate emitter voltage is less than the threshold voltage, it is in the forward blocking or cutoff region. And then as the gate emitter voltage increases, then it goes to active region and finally in the saturation region. So these names are slightly different compared to the MOSFET. But a major functional change is that there is actually a constant voltage drop in the IGBT, which is not there in the MOSFET. The MOSFET only has an RDS, but an IGBT actually has a constant voltage drop, and then it will also have this linear slope. So it also has a constant voltage drop, similar to what a diode has. So this was about the output characteristics. Then we have the transfer characteristics, again very similar to the MOSFET. If the gate emitter voltage is more than the threshold voltage, then it will start conducting, and then we have a particular slope depending on the VDS voltage as well as the temperature. Next, we have the switching characteristics, but this time I thought before talking about the switching characteristics, we can just mention how these switching characteristics are measured. So the data sheet values that are given, how they actually measure these times and energies and all these things. So it is done with something called a double pulse test. So we have uh, a circuit which is shown here, which consists of a half bridge. So that means two devices. So the lower one is what is called the device under test. It is usually you will find DUT written there. So DUT means device under test, and then there will be another device. It can be the same device or it can be another diode only device here. So they are connected in a half bridge configuration, and across this half bridge we have a DC voltage. And this is the DC voltage at which we want to test it wants to obtain the data for this device. So for example, if it is a 1200 volt device, we want to uh, get the switching characteristics at, let's say, 800 volts. So then VDC would be the 800 volts. And also we have an inductor that is connected across the top device. So now, so we have the voltage 800 volt. Now let us say we want to get the switching characteristics at a particular current, let's say 50 amperes. So what is done is the top device is kept off. So you can either connect the gate to the emitter, or you can provide a negative voltage to the gate with respect to the emitter. So then the top device will be off. So only the diode of the top device can conduct. And then you provide one pulse first to the bottom device. So the bottom IGBT, one gate pulse is provided. So if you see this circuit, if the top device is off and the bottom device is turned on, then the VDC voltage comes across the inductor. And if a constant voltage comes across the inductor, the current through the inductor will start to rise. So just like here it is shown, it will start to rise. And then when we reach the point, uh, the current at which we want to test the device, for example, if we reach 50 amperes, then we will turn off the current, turn off the pulse. If we turn off the gate pulse to this device, so the IGBT will turn off, but the inductor current will have to freewheel somehow, so it will freewheel through the top diode. So as it freewheels, after some time, and we assume that uh, the current will not drop too much, because as it freewheels, the voltage across the inductor will ideally be zero, but there will be a small voltage drop in the diode, and that is the only voltage that will come across the inductor. And then after some time, we will give a second pulse to the device under test. So then it will turn on at that current value, 50 amperes. And again, the inductor current will rise. So, and then we will turn off the pulse. So these are two pulses that are given to the bottom device. That is why it is called a double pulse test. And what happens is that at the end of the first pulse, we turn off the device at full DC voltage and the 50 amperes or whatever the current value that we want. So it is turned off at our desired voltage and current. So we get the turn off characteristics. We measure the voltage across the device, the current through the device, and all the energy that we want, all the times we can measure at that time, and that will give us the off characteristics. And then at the start of the next pulse, because we are assuming that the current will stay constant during the freewheeling time, then we are again able to turn on the device at the full voltage and full current. So basically, by with the help of this double pulse test setup, we are able to get the desired uh, current and voltage. Uh, we are able to get the desired characteristics, switching characteristics at the particular current and voltage that we want. And by varying the pulse duration, especially the first pulse duration, we can vary the current at which the switching takes place. So if the pulse duration is short, then we will get the characteristics at a lower current. And if the pulse is longer, then we will get the characteristics at a higher value of current. So in this way, we are able to get the uh, switching characteristics at different values of current and voltages. So this is the double pulse test setup. Now we can see the IGBT switching characteristics, and it is very similar to the MOSFET. So we first the gate voltage first rises, it crosses the threshold, and after the threshold, the current starts to rise, and then it reaches a Miller portion, and in the Miller portion, the voltage drops, and then after the voltage has dropped to nearly zero, then it goes again to the full voltage. But the differences from the MOSFET is that usually for an IGBT we give a negative voltage during the off time, so that we are sure that there will be no false turn-ons. So any noise that comes to the gate voltage, it should not be able to turn on the device. So we give it, that is why we give it a negative voltage. And another main difference is that during the off time, that it takes slightly longer for the gate, for the the collector current to fall to zero, and this is the what is called the tail current, and this leads to the slower switching times of the IGBT. So next we can then come to the datasheet terms very quickly. So again, yeah, by now you should be familiar with these terms. So there will be the voltage breakdown, the voltage, there will be the continuous current at different temperatures, there will be pulse current values, and the diode, which is a separate diode that is added. Its ratings are also given, the current ratings and uh, the voltage rating will be also given in the data sheet. And then the gate, the maximum and minimum gate voltage that can be applied are given. And this is the uh, name of the IGBT, the part number of the IGBT for which these data sheet aspects have been taken. Then we can also have the breakdown voltage and the temperature coefficient. So as the temperature changes, how does the breakdown voltage change? Usually it is not much. So if you see, it is 0.18 volt per degree centigrade. So after 100 degree, if the temperature changes, then it will be 18 volts. The breakdown voltage will increase, which is not much compared to the 1200 volt. Then we also have the collector to emitter saturation voltage. So instead of the RDS, what is given is the collector to emitter saturation voltage. So basically, it means that at 15 volt of gate, and if the collector current is 30 ampere, what is the voltage drop when the uh, IGBT is on? And this thing you can match from the waveform that will be given in the data sheet. So from let's say 15 volt that is given, and the current is 30 ampere. So at this point, the drop is around 1.7 to 2 volt maximum. So that is what is given here in the table, and it will match with the curves that are given in the data sheet later on. So again, then we'll have the threshold voltage, and it can have minimum and maximum values. So around 3 volts or 6 volts, if the gate voltage rises beyond this value, then the device will go into conduction. And then we have other leakage currents and the diode forward voltage drop as well. So next we can come to the switching related terms. So again, we have the gate charges and the times. What is different usually in the IGBTs, something that is not provided in the MOSFET, or at least the low voltage MOSFET data sheets, is the EON and EOF ratings, which is the energy ratings of during the switching intervals. So if when the switch, the IGBT turns on, what is the total energy that it requires at a particular voltage and current? So for example, all these conditions are given. And so we have 600 volt DC bus, there will be 30 amperes. The gate resistance is also given, which we'll see later on in the session. And this L is basically, if we talk about the double pulse test setup, then there will be an inductor. So this is sort of that L. Yeah, it can have a slightly more complicated circuit, but it basically is that L. And then at these conditions, they actually measure the voltages and currents, and then they can find out what is the energy uh, that is dissipated during the on time. And so they have given a typical value and a maximum value. And later on, they actually have different curves. So for example, as the current increases, how the E-on and E-off energy values also change. And as you can see, as the current increases, these values are also increasing. So for higher current values, the switching loss is higher, and the on energy is usually higher than the off energy because the on energy also contains the diode reverse recovery. So, so this was mentioned uh, in the previous session. So when the top diode turns off, the reverse recovery will be reflected in the bottom switch current. So that is why there will be more loss in the bottom switch. So that is why one of the reasons why the on energy is higher than the off energy. And they also provide the curves for different gate resistance values. And as the gate resistance changes, it takes more time for the device to turn on and turn off, and that is why the switching energies are also higher. And so this was about the IGBT data sheets. So the other terms like the thermal uh, terms that are given, the thermal resistances, the power loss, power dissipation, and the diode related aspects, those have been uh, covered in the previous sessions. So now we can come to the other topic that was taught in the course for this week, which is gate drivers. So the first question that can come to one's mind, why do we need a gate driver? So how do we actually drive these switches that we have? So we usually have a controller. It can be an analog controller, which means that we have different op-amp circuits or some other uh, logic gates, and we provide some carriers and some references, and then we generate the output of our controller. And that controller output will be a PWM pulse in the range of 0 to 3.3 volt or 5 volt, depending on the biasing voltage of these circuits. And similarly, the other option is that we have a digital controller, what is called a DSP or an FPGA. And similar to the analog control, it will provide us output PWM uh, signals as voltages in the range of 0 to 3.3 volt or 5 volt. So this is what we get from the controller. But now the question is, can we use these signals directly to turn on and turn off the switching devices, the MOSFETs and IGBTs? So one thing you can directly understand is that obviously uh, we cannot, a 3 volt or 5 volt will not be enough to turn on the device. So it may not cross the threshold, or even if it does cross the threshold, it will still be in, it will not go to the linear region, the ohmic region of the MOSFET or the saturation region of the IGBT. So that is why we need a higher voltage uh, to turn on these devices. So that is one problem. And another problem, if you see the controller, it will be one circuit with a ground. And if we are driving multiple switches, for example, here we have a half bridge, we have a high side switch. The high side switch is basically the one whose drain or collector is connected to the DC bus. And the low side switch is the one whose emitter or source will be connected to the ground portion or the negative of the DC bus. So if we want to drive both of these switches, we will face a problem if we use directly the controller outputs, because for the controller, both the PWM, they are with respect to the same ground. So this triangular ground that I have shown, the 3.3 volt output of the controller is with respect to this ground. However, for the half bridge, for the high side uh, IGBT or MOSFET, the gate pulse that should be given to this is with respect to its emitter. So the top gate voltage should be with respect to the emitter of the top device, which in this case is the node A, which is shown here. And if this half bridge is switching in a complementary fashion, so first one device is on, then it is off, and the other device is turned on, then the voltage of this point A will not be it will not be at zero voltage. It will not even be a fixed voltage, but it will be a varying voltage. It will be a switching voltage. It will vary between 0 and VDC. And this A point, as we see, is the emitter of the high side switch. So the gate emitter voltage will also vary. So if it is, it should vary with respect to this A point voltage. So that is why it is called a floating voltage. The voltage A is floating because it is not fixed, or it is not the ground voltage. And if we want to provide the gate pulses to the top device, we have to provide it with respect to this floating voltage. And as we see, that is, we cannot directly use the controller because it provides us both for the low side and the high side. It will just provide us 0 to 3.3. It will not take care of this floating emitter. And another thing that can be an issue is we not only want positive voltage, we also want negative voltage during the off time. So that is why we need some kind of amplification, signal conditioning between the our actual devices and the controller. So the gate driver, the function of the gate driver is basically to meet the voltage and current requirements of driving these switches. So we talked about the voltage requirements, but there is also the current requirement. So as we'll see later on, to turn on these devices, we actually require some substantial current for very small time, but it is actually a substantial value, like 1 amperes, 2 amperes. So in this range, at least for the, like, let's say 1200 volt devices, it requires currents in ampere range. But the controller, whether it is a digital or analog controller, these circuits cannot provide this much high current. They don't have the capacity. They are not designed for this much high current. And if we design them for these high voltages and high currents, then they will take up more space. They will lose more energy, and it will be a lot of power loss that is basically uh, not warranted. So that is why what we actually do is we have a gate driver between the controller and our switch that takes care of these voltage and current requirements and some other features that it provides, as we'll see. So what are the requirements? What should this gate driver provide us with? So first of all, it is, as we said, to meet the voltage and current requirements of switch driving. And that means if the controller provides us with PWM, which is between 0 and 3.3 or 5 volts, so we have to shift this voltage to plus 15 and minus 5, for example, of the gate emitter. So this is level shifting is one of the aspects that we have to do. Another aspect is the floating supply. So if the device is a high side device, like in the case of a buck converter or in the case of an H bridge, the top device of the H bridge, in that case, the emitter voltage or the source voltage in case of a MOSFET, it is not a fixed voltage, it is a switching variable voltage. So that is why we will have to provide some kind of a floating supply. So that will be done by the gate driver. Next, uh, another use that we can have of the gate driver is to provide isolation between the controller and the uh, our power circuit. And this isolation is can be for safety purposes. So for example, if there is a fault in the high power side in the side of your converter, then there should not be any path which links uh, the power side to the controller side, because uh, if there is any high current that can pass to the controller side, it will damage the controller, the DSP or the analog control. And we want to avoid that. That is why we can have an isolation. So the isolation is not necessary. So for example, the to have this 15 volt and 5 volt is actually necessary. If you don't get this, you will not be able to drive the switch. But isolation is actually technically not necessary. You can do without isolation, but we usually have isolation because it provides us with these protection features. And another thing is the high impedance input. So that basically means, like I mentioned, the controller cannot supply these high currents. So the IPWM cannot be the high current that is required by the gate driver. The IG current can be high in terms of amperes, but the controller current cannot be very high. So the gate driver should have high impedance input. That means it should not ask for very high currents. The IPWM should not go to very high values. So if you can imagine an impedance or resistance here, it should be very high so that IPWM is restricted to low values. So now we can uh, actually see how uh, the different currents and the different capacitances are charged during the gate driving process. So we have seen previously how the gate voltage changes and how the drain current and the VDS voltage changes. But now let's focus on the gate driver aspect and the gate current as well. So this VG supply that I've shown here. So let us imagine this is the output of our gate driver. So when the switch is off and we want to turn the device on, this VG basically it will go from the off voltage, which can be 0 or -3, -5, and then it will go to the on voltage, which can be 15 volt, 12 volt, or something like that. So basically, it will just go from 0 to very high uh, within a very short duration of time. So then this voltage comes across the gate resistance RG because the the MOSFET is off. So the CGS voltage, which is the voltage across the CGS capacitor, is 0 at this point. So all of this voltage initially will come across the resistor RG. So the current IG will suddenly rise to a peak value. And then as this current goes to the MOSFET, it will charge the CGS capacitor. And as it charges the CGS capacitor, the voltage VGS, it rises. So as we've seen previously as well, the voltage VGS rises. And because the voltage VGS is rising, so the voltage that comes across the RG resistance, it reduces. So that is why the gate current also reduces. And then at some time, it will cross the threshold voltage, and then the MOSFET will start conducting the current. And when it reaches the Miller plateau voltage, VGSPL here, what is shown. So at that point, what will happen is the CGS capacitor will not charge anymore, but the IG current will go to the CGD capacitor, the gate to drain capacitance, and it will basically discharge this capacitance. So previously it was charged to some value, and now the current is in the negative direction for this capacitor, so it will discharge uh, this capacitance. And because the CGS voltage remains constant, that is why uh, the gate current does not decrease during this Miller portion. And the VGS, the gate voltage also does not change. In this portion, the gate voltage and the gate current are also both constant. And as you can see, if CGD reduces and as well as the DS capacitance voltage will also fall during this time, so VDS will actually reduce. And then Again, the gate current will go through the CGS capacitance, and then the VGS voltage will rise to the full value, which is the VG value of the our gate driver actual output. So this is how the IG current will look like. So this is an approximate. Uh, these waveforms are approximate. So if you actually see, they will not have these sharp transitions and it will not be totally linear, fully constant. They will be slightly different, but this is an approximation, how to understand them and how to get some approximate values. So we can use this analysis to actually find some approximate equations. So if we want to know what is the peak value of this gate current, it will basically be the gate voltage that we are providing it through the gate driver minus if there was any off voltage that was given to the MOSFET. So if it was 0 volt, then VGS off will be 0. If it was minus 5 or minus 3, then VGS off will be negative 5 or 3. So that the numerator of this equation, it will become, let's say, 15 minus 5. So it will become 20. So the negative voltage will actually increase the gate current, the peak gate current, and then divided by the gate resistance. So then we can also try to find the gate current during the portion where the drain current is rising. And if we take the midpoint, exactly the midpoint of this region, so this TRI portion, if we take the midpoint of this region, then at that point, uh, the the gate voltage is, let's say, between VGSPL and V threshold. So let's say half of VGS, VGSPL and V threshold, and we are applying the full gate voltage. So if we want to find this current, it is the second equation that is given. And then finally, the value of the plateau, Miller plateau gate current, it will be given by just VG minus the uh, VGL, VGS plateau divided by RG. And then we can, using these values, the current values, we can actually find what is the rise time of the current and the fall time of the voltage using the capacitance values in the data sheet. So then you just use the CdVdt equation. You will find that these equations can be used to find the rise time of the current and the fall time of the voltage. And again, these are approximate equations. They will just give you an idea of how uh, around which values the actual rise time and fall time will be. So next, we can also see that during this gate driving process, there will be losses associated with this. So one loss will be in the RG gate resistance. So whatever the gate current is there will be an RMS value of that current, and that will lead to losses in the gate resistance. And then are losses due to the charging and discharging of the gate capacitances. And this P gate will actually be, you can find it from the data sheet, the total gate charge that is given. Due to that, there will be some losses. And the equation for that is given here. And these losses will depend on the switching frequency. So if you have a higher switching frequency, that means you are charging and discharging these capacitances at a higher rate. So that will lead to more losses in the gate. And these losses actually take place in the MOSFET or the IGBT, because these capacitances, these are parasitic capacitances. They are charged and discharged inside the device. So now, how to actually achieve these features in practical situations? So we want to have the level shifting, the floating supply, the isolation, uh, and the high impedance input. So how it is achieved? So one of the ways that it can be achieved is using optocoupler based gate drivers. So optocoupler basically provides optical isolation. So if we have a PWM voltage, let's say 0 to 3 volt, it is given to a light emitting diode, an LED, and that at the receiving end we can have a BJT or another LED. So that will basically turn on whenever. So there is some other circuitry involved, but basically if we have an optocoupler, we can isolate the input pulses and the output pulses. So there will be no uh, electrical path between these two portions of the circuit. So these are optically isolated. But again, you can see that it cannot, so it may be able to provide some level shifting if the right side of a circuit we have a different voltages, let's say 5 volt, or instead of 0 to 3 we can have 0 to 5 or some negative to 5 volt. But if we want the proper uh, 15 volt minus 5 volt, then we will need some other circuit. And again, this will not provide us the floating supply and the current requirement, because these LEDs are also at low current. So if we want these advantages of the high the level shifting and floating supply, we can use what is called a totem pole circuit. So what we have is, after the optocoupler, this optocoupler output is connected to a circuit that is shown here, which is a totem pole circuit, where we have uh, two transistors. So one is an NPN transistor and another is a PNP transistor. And one side, the NPN transistor, it is connected to VS plus, which in this case will be plus 15 volt with respect to the source of the MOSFET here. So this plus 15 should be with respect to the source. If the source voltage changes, then this uh, 15 volt with respect to the source will also change. So if this source is a switching voltage, then the Vs plus should also be a switching voltage, plus 15 volt. Similarly, the Vs minus is, it can be 0 volt or minus some voltage, some minus 5 or minus 3 volt with respect to the source of the MOSFET that we are trying to drive. And then once we have a PWM and the optocoupler provides this output, during the high portion, the top uh, transistor turns on, so we get Vs positive at the gate with respect to the source, and when it is off, then the bottom transistor will turn on, so we will get Vs minus at the gate with respect to the source. So it will provide us with the level shifting, and then this Vs plus and Vs minus, uh, these supplies should be able to handle the high current, so that we can get the high current, we can satisfy the high current requirement as well. So now the question is how to attain these Vs plus and Vs minus for floating supplies. So if the S portion or the uh, S terminal is floating, it is the high side switch, as we saw in the case of a half bridge, then the S voltage will also be changing. It will be changing in a from 0 to VDC. So then the supplies Vs plus and Vs minus, they should also be changing. So how do we actually attain that? So one simple way, or I mean it is simple but it may be costly, is by using isolated DCDC converters. So basically they will have an input voltage. So we can give, let's say, 5 volt input with respect to some ground, which is usually the microcontroller side ground. And then it will provide output which is isolated from the input. It will provide a plus voltage, positive voltage with respect to a common point, and a negative voltage with respect to the common point. And then this common point is connected to the source, so that the positive voltage is then with respect to the source, and similarly the negative voltage is with respect to the source. So this isolated DC-DC converter, it can be some any basic isolated converter like a flyback or a forward converter, push-pull, some other converter. And usually because these are actually available in the market in small packages that we and they're specifically specially made for the gate driving purposes. So these are available, but they may be costly compared to some other uh, solutions that we'll study later on, like the bootstrap solution. So these isolated DC-DC converters can be used to provide the supply. And in this case, we should keep in mind that the DC-DC converter should have low ripple at the output, because if we have, let's say, if we want 15 volt plus 15 volt to turn on the device, but we have some ripple in the output voltage, so it goes from uh, 12 to 15 to 16 or and 17, then the gate voltage, as the gate voltage will change, we can maybe shift from the ohmic region to the active region and the linear region, so that will create some problems. So that is why this should have low ripple at the output rate voltage, and there will be an isolation rating, and that isolation rating will depend on the VDC voltage that you are supplying, because the isolation between the input side of this DC-DC converter, it should be able to handle that DC bus voltage. So that will determine the isolation rating of the this converter, the isolated DC-DC converter. So now some important specifications about this optocoupler based gate driver. So one is the propagation delay. So if we give the microcontroller or the analog controller, it will give some PWM output, but the optocoupler cannot immediately, instantaneously take that as the input and give the same output. It will take some time, and so it will take some delay time, and then it will take some time for the output to rise. And similarly, when the input of the optocoupler turns off, it will take some time, some delay. After that delay, it will take some time to fall, the voltage to fall. So this is the propagation delay and the rise and fall time delay. And this is important when we choose the dead time, because the dead time is basically a time uh, between, let's say, the turn off the top switch and the turn on of the bottom switch. So we will give some time so that the both devices are not on at the same time. And we have to take into account the delay, because if we don't take into account the delay, it may be that we think the top device is off, but because of the delay, it is actually still on. And then we have given a delay to we have given a pulse to the bottom side switch. And this is the reason is that the rising delay and the falling delay may not necessarily be the same. If these rise and fall time delay will be same, then this problem may not arise. Uh, but because actually in practice you will see that the on time during the delay at the on portion and the delay during the off portion, they are not the same. So that is why we have to consult the data sheet of the specific optocoupler and see these delays and the rise times to make sure that the dead time is properly given. Another important specification is the capacitive coupling. So when we have the optocoupler, so ideally we imagine that there is no connection between the input side and the output side. But in practice, there are some parasitic elements. So for example, there can be a parasitic capacitance between these two. So this is not a capacitance that is put there, but it is uh, a parasitic capacitance that exists because of the dielectric between the two sides. So this parasitic capacitance, what it will do if is that if there is a difference in the absolute voltage on the two sides, there will be some capacitive currents that will flow. And these capacitive currents will create noise in the circuit it may actually turn on the one LED, and that will lead to turning on of the device at some time and some other perturbation. So basically, this capacitive coupling, uh, the value of this parasitic capacitance is important. And this is given in the data sheet what uh, they have measured, the manufacturers have measured this kind of a capacitance to be. And lastly, the third point is what is called the common mode transient immunity. And this is also related to the previous point. But if you see, for example, here in this circuit, so as we mentioned, if we have a half bridge, the switch node, which is the midpoint of the half bridge, the voltage of this region actually changes from 0 to plus VDC to again 0. And this will actually take some time for the voltage to rise. Like that will be basically the given in the device data sheet, the rise time and the fall times. And because it takes some time, and as we saw, there is some parasitic capacitance, uh, they will create some parasitic currents, and that will actually they can create problems for the gate drivers. So that is why the gate driver is actually rated for uh, some common mode transient immunity, which means that uh, how much the uh, the DC bus changes or the switching node changes based on this VDC voltage and how fast it changes. So how many nanoseconds or microseconds does it take? Based on that, we will have a rating, DVDT rating, and the gate driver should be able to handle that rating. So if that rating, the rating of this, the CMTI rating of the gate driver should be higher than the DVDT of your application, whatever your DC bus voltage is and how much time it takes for the voltage to rise and fall. The gate driver should be able to handle that uh, that transient. So it basically depends on the VDC voltage as well as the voltage rise time and fall time, and it is measured in kilovolt per microsecond or kilovolt per nanoseconds, and you will find it given in the data sheet of the gate drivers. So this was about the summary of what was taught in the week. And as I mentioned, the DSAT we can take up in the next week's session. So now we can come to some problem solving. And before we start, we can actually take a short break. So it is 3:57 right now. We can begin at let's say 4:05. Okay, some 7-minute break.
Okay.
Okay, so let us continue. So in these first few questions, I will actually ask you to uh, guess what is the answer, or if you know the answer, you can just tell the answer in the chat. You can just write A, B, or C. So the first question is, which of these functions as the Miller capacitance of in MOSFETs? And you basically have the three capacitances of the MOSFET as the options, whether it is the gate to source capacitance, whether it is the gate to drain or drain to source. So does anybody know the answer? So you have to know what is the Miller portion or the Miller region, and then which of these functions as the Miller capacitance. Okay, so we can basically see, as we uh, saw previously, what is how the turn on process of the MOSFET is. So if we have these three capacitances, and when we apply the first voltage, first of all, the gate source capacitance starts to charge. So the first portion, that is from 0 to the Miller portion, so that is in that region, or in during that interval, the gate source capacitance is getting charged. And after it reaches the Miller value, so the gate source Miller voltage, after that uh, it stays constant for some time, and during that interval the gate current actually goes through the CGD capacitor, the gate to drain capacitance, and that capacitance gets discharged during the turn on process. So during the Miller region, the CGD capacitance is actually the one that is uh, getting discharged. So that is why this is called the Miller capacitance. So, and thereafter again the CGS capacitance gets charged. So then after the Miller region is over, then we again go back, the VGS again starts to rise. So the answer to the first question is the gate to drain capacitance, which is the CGD capacitance. That is the Miller capacitance in MOSFETs. So the next question is, a MOSFET is in which region when the gate to source voltage is less than the threshold voltage? So this should be known. So can anyone guess what is the answer? A, B, or C? Your options is the cutoff region, the ohmic region, or the active region. And the condition is that the gate source voltage is less than the threshold voltage. Yes, so it is basically quite simple that we have these three regions. The forward blocking is basically when the gate source voltage is less than the threshold voltage. It is called a blocking region or the cutoff region. And as it gate source voltage rises, then we can come first to the active region. In that region, uh, the current is limited, and if we want to go for higher currents, we will not be able to. The VDS will start to rise. But as we increase the gate source voltage, we can go to the ohmic region, and in that region, we can go to very high currents uh, for very low voltage drop. And the ohmic region and the cutoff region, these two are the regions that are used in power electronics because we have very high voltages and high currents. So that is why we cannot go into active region. It will cause a very high power loss. So the answer to this problem is cutoff region. So similarly, now an IGBT enters into which region when the gate source voltage reaches the threshold voltage. So now it has reached the threshold voltage. So actually for the IGBT, so it should not be ohmic, sorry, it should be the saturation region is the third option. But the answer is basically the active regions because once we reach the threshold voltage, we come to the active region. And then for very high voltages, then we will go to the saturation region. So just if we just cross the threshold voltage or just reach the threshold voltage, then the IGBT will start to conduct, but it will be in the active region. So the answer to this one is C, the active region. Now the fourth question, and this is, we just talked about this. If we have a floating supply, it is required for uh, which switch in the H bridge converter. So if we have an H bridge converter, one leg of the H bridge converter, so we have two switches. One is the high side switch, another is a low side switch. So for which one do we require a floating supply? Yes. So this is because for the low side switch, which is the bottom switch, the emitter or the source, if whatever the device we have, is directly connected to the negative DC bus. And this voltage does not change. It remains at its potential. So if we have a gate driver for the low side switch, then the gate voltage should be with respect to a constant voltage. But for the high side device, since the emitter voltage, which is the switch node voltage, actually changes between 0 and VDC, so we require a floating supply for the high side switch. So, and so we can, if we don't have a floating supply for the bottom side, that is fine, but we need a floating supply for the high side. So, so the answer is for the high side switch. Now we can have an isolated supply for both, but it is only required for the high side. But we can have it for both as well. So the next problem is which of the following uh, are true while a MOSFET or IGBT is turning on. And the options you have is that during the Miller period. So the question is asking about the Miller period, which we just saw. And the first option is that the gate to source voltage becomes constant. The second is that the gate current is constant. The third is that the drain current rises. And the fourth option, D option, is the gate to drain capacitance discharges from blocking voltage to on-state voltage drop. So which of these is true? So there can be multiple answers which are true here. Okay, it need not be just one of these four. It can be two or three or even all four. Okay, so based on the chat, at least D should be true, and some are saying A is also true. Yes, so ABD, so that's a good answer. So if we again go to this circuit, we see that during the Miller portion, the gate current actually goes through the CGD capacitance. So since the since it does not go through the CGS capacitance, VGS voltage will remain same. So that is basically the A option. A option is true. VGS voltage does not change. Then since VGS is same, then the current will also remain same because the current is VG minus VGS divided by RG. So the current is also same. That is the second option, I think. That is also true. And since this current is then going through the gate to drain capacitance and it is getting discharged. So first it was charged to the off-state voltage and now it is getting discharged. It will just be the forward blocking voltage. So that is the D option. And the C option was the drain current rises, but as we see, the drain current is actually already risen to the full value before the Miller region. So it rises from the threshold to the Miller voltage. So it is already risen to the full value. So the C one is not true. So that's why the answer to this is A, B, and D. And the next problem is In a gate driver circuit, the RMS value of the gate current is dash with respect to the peak value of the gate current. So is the RMS value of the gate current equal to the peak value of the gate current? Is it much higher than the peak value, much lower than the peak value, or slightly lower than the peak value? So this we actually did not talk about yet in the session, but it was covered in the course. And so basically you're talking about the RMS value of the gate current. Yes, so if we see this is the gate current, and as we saw, the IG peak is given by VG, the peak of the VG divided by RG. And let's say, as we'll see, VG can be 10 volts or 15 volts, and RG is usually, I mean, it can vary a lot. But let's say if it is 5 volts, 5 ohm, then the peak gate current can be 2 or 3 amperes. But what about the RMS of this value? So we are seeing this current in a very short duration. But if we zoom out, basically, uh, what we'll see is that as the uh, switch is turned on and off, the gate current is only there for a very short duration of time. When it turns on, when the switch turns on, then we have a positive gate current, and when it turns off, then we get a negative gate current. And the peak value can go to a few amperes, but then it quickly falls to zero because this time is just the switching time. It can be in nanoseconds, while the whole duration is tens of microseconds. So that is why we will have these portions are very small timed portions, and we have a positive and negative portion. And if we find the RMS of this current, it will be actually much lower than the peak value. And I hope you can understand it from this waveform itself. You don't actually need to do the RMS calculations to know that it will be much smaller than the peak value. So it will not be equal, it will not be higher. It will be lower, but now the question is whether is it slightly lower or is it much lower? And since it is zero for most of the duration of the overall cycles, then we can say that it is much lower than the uh, peak value of the gate current. The next question is a totem pole. We have a combination of NPN and which other type of transistor? So is it another NPN, or do we have a PNP? Do we have a PN junction like a diode or something?
Sir, what is totem pole? Pole?
Okay, so totem poles is basically uh, this portion of the gate driver circuit. So we have two transistors, they are connected in a particular way, and the base portion of both of these transistors is from the same uh, supply. And so this kind of a connection is called a totem pole. And this totem pole connection is used in gate driving after the isolation, after the optocoupler. And so we
Okay.
will have one NPN transistor and another PNP transistor. And when we give the same uh, base supply to both of them, so when we have a high pulse, the NPN will turn on while the PNP will remain off. So we will get plus VS plus at the gate. And similarly, when we have the PWM is low, then the PNP will turn on. So we get VS minus at the gate. So the answer to this question is basically PNP. If we have NPN, the other one should have to be the PNP. And I mean, this is one realization of a totem pole. You can have it with, instead of BJTs, you can have JFETs or some other device as well.
Got
Okay, so next question is based on a data sheet. So it is similar to the questions that you have been given in your assignment. So you have to consult a data sheet and you have to find some values from the data sheet. And in this question, we have been asked to find the value of the gate resistor that is used by the manufacturer to measure the turn on and off times. So if you search for this data sheet and you find the turn on and turn off times, at the end you will be given the conditions under which these have been measured. So we have there is a VDD, which is basically the DC bus, and there is the drain current. So again, this will be some kind of a double pulse test setup or something like that, similar to that. And so we have a DC bus, we have a drain current, and they give the gate resistance RG, and they also provide the gate to source voltage. So the question is basically asking about what is this RG, and the RG here, if we see from the datasheet, it is 5.1 ohm. So the next question is asking about the same MOSFET. From the datasheet, we have to find the maximum value of the total gate charge. So the gate charge is basically given in the datasheet tables, as well as there is a figure about the gate charge. And from the figure, you can see it is given for different drain to source values. Uh, and as the drain source voltage increases, the gate charge will also increase, but only very slightly. And for the maximum voltage 80 volt, it is given that this gate charge is very close to 70. But if you see from the table, it is actually 71. So, and the question is asking about the maximum value. So the value of this would be 71. And again, there are other charges as well. So first one would be gate to source, and then the Miller charge, and then the rest, which is again goes to gate source, but it is not given separately in the data sheet. So the answer to this one is just 71 nanocoulombs. And just make sure you take into account the unit that is given in the question. You only have to provide the numerical value in that unit. So now the next question is basically, if we use the same RG value as used by the manufacturer, which we just saw is 5.1 ohm. Now the question is asking us to calculate the IG peak. And the question is also giving us the peak value of the gate voltage, or the gate voltage that will be the output of the gate driver. That is 15 volt. So now this calculation is very simple. Again, we see from the data sheet, the RG was 5.1 ohm. So based on the 15 volt gate driver, or the 15 volt gate voltage that we provide, and the 5 ohm uh, gate resistance, we will get a peak gate current of around 3 amperes, so 2.94 amperes. And you see 3 ampere current, uh, the microcontroller or the analog controller, it will not be able to provide this high current. So someone in the chat has got 3.92, but I'm not sure how you will get that. If the gate voltage is not provided in the question, uh, then then you basically don't have all the information, but then you can either take this value, but I think in your assignment you have been actually provided. So you have been given a situation where you have like a buck converter, and you have been given the switching frequency, and you are also given the gate voltage. You look for the gate voltage at that portion, and it may not be given in the actual some problem number, but previously it is given in the top of the assignment. But if you're not given it, then you can take this value that is given in the conditions. So what I was trying to say was, it is a very high current, and that is why we require some more circuitry, some gate driver to provide this current. Uh, but again, this is just the peak current. After that, it falls to zero, and it remains zero for most of the duration while the device is operating. So the next question is the same MOSFET. Now we saw that the current was around 3 amperes. Now if we want to limit it to 1.5 amperes, what should be the value of Rg in ohms? So obviously if we want to limit it to less than uh, what we got previously, we have to uh, basically increase the gate resistance. So the question actually says 1.5 amperes, but here it should be 2 amperes. So let me just actually change it. So the IG peak has to be limited to 2 amperes from 2.9. So now we have to find the value of Rg. So the Rg comes out to be 7.5 ohm. So this basically means if we have a particular gate driver and the gate driver has a limited peak current rating, let's say if the gate driver is limited to 2 amperes, then you will have to use a higher value of Rg so that the peak gate current is less than 2 amperes. So someone in the chat is asking 15 and then minus 5 voltage, but you're not given the minus 5, you're only given the plus 15. So if you're not given a negative voltage, then you have to assume that it is 0. But if you are given a negative voltage, then you can take it into account for your calculation. So I hope that's clear. Someone is asking to explain the previous question. So which one? The one that was before this, the gate charge one? Okay. Yeah, so the question is simply asking about the maximum value of the total gate charge. So as we saw, while the switch is turning on or off, we have to first provide some charge for the VGS capacitance, and then some charge goes to the CGD capacitance, and then again back to the CGS capacitance, the voltage rises. So the total charge that has to be provided is called the gate charge. And the question is asking about the maximum value of this gate charge. And that you can just simply find from the datasheet table. The total gate charge and the maximum value that it has is 71 nanocoulomb. So the answer is just simply from this. But now you can look for other things if you want to see that this was taken at a particular conditions, and as the conditions change, the gate charge value will also change. So if the VDS change from 80 volts to something less than that, then the gate charge will also change. But for the answer, it is just simply from this table you take the maximum value of the total gate charge. So I hope that's clear now. Okay, so for this one, again, I'm just repeating that if VG is given as 15 volt and then you're not given what is the off value, you assume that it was 0. If it was a negative value, then it must be given. Otherwise, I mean, how will you know what is the negative value that you have to take? So that is why for the calculation, I'm just taking 15 volt positive. So, so if you want to limit the current to a particular value, then we have to change the Rg value accordingly. So this was all the questions that we had. Yes.
So from the previous question, how the 15 value came?
The 15 value is actually given in the problem. So this 10th problem is a continuation of the previous problems, that is 8, 9, and 10. So we take
Okay.
the 15 volt from that. So for example, in your assignment, I think at the top it is written that for some questions, there is a situation that you have been given from, let's say, question number 10 to 20. And that situation is written that you have a buck converter, you have to get a gate driver, and this is the MOSFET that you are using, this is the switching frequency, and this is the gate voltage. So you take that gate voltage for all those questions. Okay. So any other questions regarding this today's subject? The power required to drive the MOSFET. Uh, okay, so we talked about it slightly. So it is based on the gate charge. So uh, so basically the power that is lost during the gate driving is there. It has two components. One is the RMS of the IG, and as we saw the IG RMS, it will probably be very less. But still, if you calculate that value, you can take into account uh, the loss in the gate driver, in the gate resistance, and then there is some power required to charge and discharge the MOSFET, and that is basically given from the that can be calculated from the uh, total gate charge, the QG value, and you also need the voltage. So once you have these two values and then the switching frequency, you can find out the power required to drive the MOSFET. So someone has their hand raised. Yeah, you have a question you can ask. You can unmute yourself, but you are already unmuted. So everybody is able to unmute. Uh, so if you have a question, you can ask you can unmute yourself and you can ask. The application of optocoupler and gate driver. So can you elaborate the question? What do you mean the application? You want to know what is the application of optocoupler and gate driver? Optocoupler has,
Sir, my
yes,
sir, where is using to for about calculating the RPM or something, sir. Optocoupler.
calculating the RPM.
Yes.
Uh,
I want to know. Yes, my question application where to use the optocoupler and gate driver, sir.
okay, so the optocoupler can have many applications. So it is basically something if you want an isolation for this low voltages, then you can use the optocoupler. It can have many applications, and that depends on what you're trying to do. But here we are using the optocoupler for gate driving purposes. And gate driving and the application of gate driving is just to drive the different MOSFETs and IGBTs that we require. So that is the whole point of gate driver. So there is no other application as far as I know for gate driving. But optocoupler can have many applications, and that is not really something that you will be asked about, I think. You just have to know how optocoupler is used for gate driving, and that we have uh, studied. Basically, it will take the controller input as controller output as the input, and then it will isolate it from the controller. So someone is asking that -5 voltage is must, but again, it is not a necessary condition that you have to give the -5 volt. It depends on many things. It
But
depends.
to
Yes.
fully turn off the IGBT, we must apply the negative volt, right? So it is not mentioned in the datasheet. Usually in practical, we do not apply 0 volt to turn off. We apply the negative volt to turn off the IGBT, right?
So again, it depends on. So first of all, the question was about MOSFETs, and I think the same is the case with your assignment as well. Uh, so you have to take into account whether it is talking about MOSFET or IGBT. And then even in MOSFETs, for SiC MOSFETs, normally now we use negative voltage, but low voltage Si MOSFETs, it is not needed that we will give a negative voltage. So unless you have been told, I will suggest that you do not take a negative voltage randomly. So unless you have
Okay,
been specifically told that this is the negative voltage that is applied, because I believe in the course as well, you were told that the MOSFETs have to be, they do not need negative voltage, and IGBTs we usually give, but then again,
okay,
you will have to be told what is the value of the negative voltage.
okay.
Yes, so it is I square RMS into RG. Yeah, that is what is written here, right? Yeah, the first term is dissipated in the gate resistance. The minimum power rating of the gate driver IC. So that is one of the assignment questions. So want to you want me to answer but basically it is this power, the PG loss, the full power, that is the gate power plus uh, the power that is lost in the resistance, that the gate driver IC must be able to provide. So that will not be given in the MOSFET datasheet directly. So you have to see the gate charge, you have to see what voltage you are applying, you have to see the switching frequency, then you can find the P gate, and then if you have the gate resistance and you know the RMS value of the gate current, after that you can find the PG loss, and that will be the minimum power rating. So I hope that's clear. Yes, someone has any more questions?
Sir, is there any particular method or formula to calculate the deadband, or it is just random based on the turn off time, turn on and turn off time?
Uh, yes, it is based on the turn on and turn off time. I mean, I wouldn't call that random, but I mean, there are some papers people have, they want to optimize the dead time, but there is no specific general rule that everybody follows. But basically, it is based on the on time, off time, and you will give it because the on time and off time they will also change based on uh, what the current is, voltage is, temperature is. All these things will affect the times. So you give some extra dead time to account for these things.
Can you please guide the any thumb rule if let's say turn on and turn off total time plus 20% margin or 50% margin is sufficient in practical case?
Yes, I think uh, even 50% margin can be good enough. But then you also have to see whether it should not take too much of your duty portion. So if your switching frequency is high and you give a long dead time, then that will take away from your duty. So you have to, I mean, you take, let's say, the rise time and the delay time, and you 1.5 times. That is a good starting point, and then you can see whether if it affects your the on time, the total on time of the switch. So, for example, if you're from the data sheet, you get the total time for the on time and off time. It is, let's say, 100 nanoseconds, and you're switching at, let's say, 100 kilohertz, which is 10 microsecond is your full time. Then you can given even two times uh, the data sheet values. If you give 200 nanoseconds, that will be a safe value. You will not have any problems, and that will not take away from uh, the duty much, because during the dead time the diodes only will conduct, and diodes usually have more forward by drop than the MOSFET. So that is why we don't want the dead time to be too much. But yeah, 1.5 times, that is a good starting point. Okay, so if there are no more questions, then if anyone wants to leave, they can leave. I'll be here for some more time. And if anybody has any questions, you can write in the chat, or you can unmute and ask on the microphone. Okay, thank you all for joining.